Hello, this is Tim Malloy with my and Danny Gleeson and I's Capstone, which is physics plus baseball. How can we apply what we learned in AP to a baseball bat hitting a ball? So there's kind of two parts to this. The first is just exploring kind of the energy behind a bat and ball hitting, talking about like collisions a little bit, and then the second part is exploring the center of percussion. So if I were to say what two topics we'd be bringing together, it would be energy and rotation. So we know, or we can, assume just by looking at a baseball game that energy is transferred very quickly. Think about how quickly a ball goes from heading towards the batter. I know this is bad. Think how quickly a ball goes from heading towards the batter to being launched towards the stands. There's a very quick transfer there, very quick change in velocity. So let's use an LOL to model the energy in a baseball bat system. So first I will explain part A, then B, then we'll watch a video, and then we will see part C. And I said, let's say that the vertical position is constant because I want to focus on elastic and kinetic energy. So in part A, we have the ball just flying through the air post-throw, and the batter has not swung yet. And then for part B, I say that the batter swings, and so at the instant the ball is hit, the ball compresses in the bat, which is where this elastic energy comes from. And this compression into elastic energy and decompression back into kinetic occurs in just 1 millisecond, and it's extremely hard to capture, on video, even if you're recording at, say, 120 frames per second. And the kinetic energy that's still present on this graph represents the ball and bat still moving in one direction, mainly, the bat. And you might notice that some energy is missing. I'll explain that in the next part, after I explain part C. So let's watch this video of that part B motion. Again, it happens very quickly. You can see the bat is still moving and the ball is compressing there. There you go, it just flies away. We'll do that one more time. It's kind of satisfying to watch. It's kind of crazy how that ball compresses like that. The human eye can't even see it. So post hit part C, we have just really focus like the instant after the ball is hit. So that's the instant the ball is hit. Instant after, we have all kinetic energy in the baseball swing and the baseball swing and the ball moving. Also, again, there's energy loss. So you can see I have 3 boxes in part A, and then I should be getting 6 boxes in part B, but I only have 2. Why is that? Why is energy lost here? The collision is inelastic. There is energy lost, in the collision. The collision is not perfectly inelastic, or else the ball would stick to the bat. And that lost energy can often be found in the batter's hands. They usually sting after hitting the ball. We know with elastic energies that there is energy not conserved, and that is kind of because the energy goes somewhere else, whether it be sound or that sting, that like resonance, that frequency, that vibration that happens after the collision. And if only there was a way to reduce that sting. And we looked into that. So Danny and I researched the sweet spot of hitting a baseball. We hoped there was a part of the bat where the ball flies the furthest, the hand stimulates, etc. There is no such point. It's different for each part we want to maximize or minimize. And the center of percussion is the point that will result in the least hand vibration. If the ball is hit at this point, there will be a zero net force at your hand's pivot point. I thought of it kind of like balanced rotation. Please note that the arrows are not to scale. So as your hand rotates, I guess you could say rotates the bat or swings the bat, the ball hits the bat, and it almost feels like there's you're just kind of, I guess, hitting, like, you don't feel how do I put this? You don't feel like the bat is really like being like interrupted in its motion. It feels smooth. It's a smooth hit. So there's a formula for center of percussion, or some, I'll just type into it. B is the distance from the endpoint, or your pivot point, on the bat to the center of percussion. I, moment of inertia. P is the distance from your pivot point to the center of mass. And then M stands for mass. This is a pretty cool formula. It's an example sure they won't be too hard. Well, to kind of stay in the scope of what we've learned in this first semester, we're going to make some simplifications. So, for this bat, look at that mass distribution. That is, I'm not even quite sure where to start. I suppose I would chop the bat into parts and kind of figure it out, which wouldn't be too hard. But then you have, the parts where the bat kind of curves, and then you have that nub, and let's just use a uniform rod instead. And let's also grip the bat at the very end of the nub. Oh, I'm sorry. And then I did my example in Notability, so I will go over there right now. Okay, it's frozen right now. Just give me a second. Thank you. Okay, a bat has the following mass and length below: 1 kilogram and 9 meters. It is swung at the knob of the bat point flat. So we're going to let the moment of inertia equal 1/3 mr squared. So let's find the bat's center of percussion. So we know through center of percussion formula, we're going to need a distance from endpoint to center of mass. So let's find center of mass. Mass times the total mass of the bat times, I guess, the middle of it. So 0.5 meters over total mass is 0.5 meters. Moment of inertia, we plug in our values for mass and length to get that. Center of percussion, we have moment of inertia, plug that in. We have mass, plug that in. And so if I was to find the distance from the pivot point to the center of mass, that would just be L over 2. So 0.9 m over 2. Again, like I said, center of mass, 45 meters. So then we have our center of percussion is at 0.6 meters, which is, I like drawing, which is at this point, it is two-thirds down the bat. So that's a pretty cool calculation that we just did there. And some takeaways: it's a very complicated process to completely or like properly find the center of percussion, because you have to take into account the mass distribution and then find the rotational inertia at the at your pivot point. So it's really only practical in a lab scenario. I'm sure real baseball players, they just kind of are told about where they should be hitting the ball. And a decent portion of the capstone was developed using a website by a Penn State professor. I think I have that. I'll just show. It's kind of cool. It's loading right now. So he's just got this whole website, physics and acoustics of baseball and softball bats. It's pretty crazy. It's from 2008, but it was very useful in developing this. There's some stuff that is kind of beyond my understanding, but what I was able to make sense of, I kind of tried to dumb down for an AP level. And as you move your grip inwards, the center of percussion travels towards your hands. So thank you for watching. I kind of tried to, Danny and I kind of thought to try to explain this as if it was like gravitation or oscillation, where it was just kind of building off what we already, knew with our rotation. So kind of think of it as like another AP topic. Okay, thank you for watching.